So in the last lecture, we discussed Euler paths and Euler circuit, right? So what is an Euler path? Euler path is a simple path which travels through all edges of the graph. Okay. When it comes to the Euler circuit, it is a simple circuit which travels through all edges of the graph. And remember one thing, we do not define the Euler circuit from Euler path. Like having Euler circuit, it is not same as having Euler path. Like if you have a simple circuit definition is defined like this: a simple path which start and ends at the same point. But when it comes to the Euler circuit, we are not saying that an Euler path. Okay, we are saying that it is a simple circuit which travels through all edges. That's what we are saying. So having Euler circuit is not same as having Euler path. So treat them, both are different. Euler path is different and Euler circuit is different. So the only common property is both are traveling through all edges. Okay. Right. So now let us discuss about Hamilton paths. So far we discussed about the paths which travels through all edges, or the circuit which travels through all edges. And we have seen necessary and sufficient conditions for that. So we know that the Euler circuit exists when Euler circuit exists if every vertex is of even degree. If you have every vertex is of even degree, then it is possible to find an Euler circuit. But how about Euler path? You need two vertices of odd degree. Then we can guarantee that there is an Euler path, right? So these are the two theorems we have seen for Euler circuit and Euler theorem, necessary and sufficient condition. And also we have seen a procedure to construct an Euler circuit or an Euler path. Okay, for Euler circuit, what you have to do is you just identify the simple circuit first. Then you try to eliminate the edges which involved in the simple circuit, and again you find another simple circuit which starts at any one point of the previous circuit. So like that you are going to find the Euler circuit. All right. Whereas to find Euler path, what you are doing, to find an Euler path, we have to see the simple path first. In the step one, you start with simple path, and then later on, you try to find the simple circuits. Okay. So now you join all of them, then you are going to get an Euler path. So these are the algorithms we are following to find Euler paths and Euler circuits. Okay. Now let us talk about let's talk about the graphs. I mean the paths, simple paths which travels through every vertex of graph. So earlier we are concentrating on edge. Now we are concentrating on vertices. Okay. For example, you take this graph. Of course, the graph has to be connected. If it is disconnected, you can't find a simple path which goes to all vertices. Okay. For example, if you consider this graph here, the graph itself is showing a path which travels through all vertices of the graph. So it has simple path, travels through all vertices, and even this also has simple path, but it may not go through all edges. Our condition is we need a path which go through all vertices. That's it. It's not needed that you need to travel through your edges also. Okay. So either you can consider, suppose if I take this as A, B, C, D and E, you can take A, B, C, D, E. Okay. So it means I'm going this way and then to E. So this is one simple path which goes to all vertices. And another simple path which goes to all vertices is A, B. Okay, it means I'm going on. So can I have another simple path? Yeah, I hope we can. You start at E, E, D, and then A, B, C. This is another one. Okay, it means first you moved along ED and next EA and next AB, BC. That's it. You are not traveling on this edge. Okay, now this is another simple path which goes through all vertices of the graph. Now let me look at another graph. So does it have any simple path? Yes, it has. It's like you start at this point and set 2, 2, 3, 4, 5. So this way you can easily go. All right. Now I need a graph which does not have this path. I mean the path which travels through every vertex of the graph is called Hamilton path. So if it travels through the edge, we call that as an Euler path. If it travels through all vertices of the graph, we say that that path is Hamilton path. Okay. So now I need an example of a graph which does not have Hamilton path. So let's do one thing. Let me take the graph contain isolated vertex. Okay. Now what I wanted to do is I'll take one vertex here, we'll connect it like this. So does it have an Hamilton path? A path which travels through every edge of the graph and no edge is, we are not allowed to repeat any edge. Okay, for example, if you start here, let me name it like this. Yeah, A, B, C, D. Yeah, after going here, now there is a dilemma. Like, do you need to go E or F? Okay, suppose if you move to E and you're not allowed to come back to the vertex D. Okay, so is this graph connected? This graph is connected, but we do not have a simple path which is passing through all the vertices. The graph has simple path, but the problem is it is not passing through all vertices of the graph. All right. So whenever you have two pendant vertices, then we can say that suppose if the graph has more than 3 vertices with two pendant vertices. Okay, then in that case we can say that it cannot have a Hamilton path, right? For example, I'm saying more than 3 vertices and two pendant vertex. So if I say two pendant vertex, definitely. So this is how the graph looks like. And you can have, I'm saying more than 3 vertices. So let me restrict to 4 vertices now. Okay. So in the case of 4 vertices, so the max, if the graph is connected, I can go this way. That's it. If it is a simple graph, whereas if it is a multi-graph, then you may have multiple edges like this. Fine. It actually has 3 pendant vertices, not 2. It has 3. Okay. If I go for one more vertex, then I can make exactly 2 point vertices. All right. Now we are very sure that this graph do not have Hamilton path. All right. Now let us see what is a Hamilton circuit. So what is Hamilton circuit? It is a simple circuit which passes through every vertex of G exactly once. So that is what we define as Hamilton circuit. Okay. For example, if I take this graph like with 2 pendant vertices, so does it have a Hamilton circuit? First of all, if there is pendant vertex, we can't. We can easily say that it has no circuit. I mean, no circuit which passes through all vertices. That may have a circuit, but suppose once if you reach this pendant vertex, okay, you can't go back. That's the problem. So we can't have a closed circuit which passes through all the vertices of the graph. So this doesn't have Hamilton circuit. Okay, how about this one? I'm not done with the graph. You're giving thumb up, right? So I'm not done with graph. Yeah. So now you tell me. How about this graph? Does it have a Hamilton circuit? Okay. So what is it? So let me name these vertices as 1, 2, 3, 4, 5, and 6. Okay. So tell me the simple circuit here, which pass through all vertices of the graph exactly once. Let me start with 5. Suppose if I start with 5, then you can come to 6, then to 2, then to 1, then 1 to 4, then 4 to 3, and again you will come back to 5. So, okay, can you start at 1? Yeah, I hope you can start at 1 also, no issue. By starting at 1, 2, 6, 5, then 6, 5, and then come to 3, then to 4, and come back to 1. Okay, suppose what if I don't have this edge? Yeah, circuit means the starting and ending vertices must be same. So suppose if I don't have that edge in the middle, then suppose if I start at 5, then we can come to 6, 2, 1, then yeah, then you may not move to 3, but if you go to 4, there is no way to go back to 5. So there is a problem. So if you don't have this edge, then it doesn't have Hamilton circuit. Okay. So by removing this simple edge, we are we are making this graph as no Hamilton circuit, right? Okay. So like in the Euler case, do we have any theorems that guarantee uh, Hamilton paths or Hamilton circuits? So in the case of Euler, okay, wait, there is a question. According to the definition, we just need to reach what is the, we just need to reach every vertex. Yeah. circuit means starting and ending vertex is same. So we are visiting a vertex twice. Okay, there is an exception for the starting vertex. There is an exception for the starting vertex. Okay, the other vertices, the middle vertices, whatever you are getting, that has to be traveled exactly once. That's what they mean. You understand? For example, when you draw a circuit, okay, so let's do one thing. Let's draw the circuit here and let's try to understand. For example, if you have a circuit, it means it can be drawn as a cycle, right? Like this. The moment it is a circuit, then it can be drawn this way. Now, how many times can you see each edge here? Each edge can be seen only once. Okay, that way you try to consider. All right. We need to reach the starting vertex. We need to reach. We are saying a simple circuit which travels to every point once. You can have an exception for the starting and ending points. If you feel like you are coming back to the same point, so it is twice, then we have an exception for that starting point. Okay, but in general, if you see that entire circuit here, like that, like this, you can see each vertex is occurred only once. This way you try to understand. Okay, maybe in the definition, it's good if we keep the circuit has an exception for the starting point. Okay, that you can visit twice. All right. Now, in the case of Euler circuits, we have a necessary and sufficient condition. It means if the circuit is Euler, then we know that every vertex is of degree 2. If every vertex is of degree 2, sorry, not degree 2, even degree, and if every vertex is of even degree, then it has Euler circuit. So we have necessary and sufficient condition. In both ways, we are able to say about that condition. Similarly, for Euler paths. For Euler path, what is it? We can find two vertices of odd degree and rest of the vertices are of even degree. All right, it is true in both ways. But when it comes to Hamilton, we don't have a necessary and sufficient conditions here. Okay, but we have sufficient condition. And also we can say that when it cannot have Hamilton paths or Hamilton circuits. When it comes to Hamilton path, we already discussed. If you have two pendant vertices, it cannot have a Hamilton path. Okay, let's say if you have two pendant vertices, yeah, we are sure that there is no Hamilton path. All right. So here you can see a graph with a vertex degree 1 cannot have Hamilton circuits. So this is about Hamilton circuit. Earlier I'm discussing about Hamilton path. This is not having Hamilton path. Whereas if you have just one pendant vertex, yeah, it's not possible to have a Hamilton circuit. Okay, if there are two, then no Hamilton path. And one more thing they are saying, if let's say if you have a vertex of the graph of degree 2, then both the edges incident with it must be included in the Hamilton circuit. For example, you have a graph like this. Okay, let me take the previous example. Okay, so here let's see what are the degree 2 vertices. So this is of degree 2, it is degree 2, and this one and this one. So we know that it has a Hamilton circuit. Okay, if you construct a Hamilton circuit here, then the two edges incident with degree 2 vertex must be included in the Hamilton circuit. Okay, let's see. Let's see the possible Hamilton circuits here. We have already written the starting at 5, that is 5, 6, 2, 1, 4, 3, and 5. But something I think I'm not getting, for example, oh, sorry, the 3 is not of degree 3. 3 is not a degree 2. And this is also not of degree 2. This is of degree 3, and this is also of degree 3, no? And these two are degree 3 vertices. Okay, there are only 2 degree vertices. Now you can see that in the Hamilton path, in the Hamilton circuit, this vertex and this vertex and this vertex, all these vertices are included in this Hamilton circuit. Okay. Yeah. And there is one more condition, Hamilton circuit cannot contain a smaller circuit within it. All right. Because we have a condition, right? What is the condition? Every vertex needs to be visited only once. If every vertex needs to be visited only once except the starting vertex, then we can't have a sub Hamilton circuit in a Hamilton circuit, right? For example, here the vertices are except the first and the last, no one got repeated. Then only we say it is a Hamilton circuit, otherwise it is not. Okay, let's assume that we have a Hamilton circuit inside an Hamilton circuit. It means what? It means in the middle vertices you can find at least 2 guys. They are same. Okay, you may find some A here, some B here, so that A equal to B. Suppose if you find such vertices, can it be a Hamilton path? No, it cannot be. Therefore, we are very sure that Hamilton circuit, it's not a Hamilton path. So Hamilton circuit cannot contain a smaller circuit within it. Okay. So you take a complete graph now. So does every complete graph has Hamilton circuit? I showed you the statement initially. Now you say that the answer is yes. Every complete graph Kn has Hamilton circuit whenever n is greater than or equal to 3. If n is equal to 2, we cannot have a Hamilton circuit, no? Because uh, it's not, there's no circuit first of all. Alright, what is that Hamilton circuit in Kn? What is the Hamilton circuit in Kn? Okay, or tell me one Hamilton circuit in K1. You may have more than one Hamilton circuits, but in Kn, what is the easiest Hamilton circuit? Yeah, it has a name, no? If it is 1, 2, 3, 4, 5 up again to 1, we call that as it is a special type of graph. What is its name? I am asking its name. That's a cycle, no? Cn. For example, you take a complete graph with 5 vertices. Yeah, so this is a complete graph with 5 vertices, right? Now the simplest Hamilton circuit you can see is, right, 1 to this, and then to this, and then to this. That's it. Okay. So Cn is 1. So that's it. For every Kn, we can easily say that Cn is Hamilton path. That's it. Cn itself is giving us. There are some other Hamilton circuits also. Okay. So now, okay, if you are interested to count the number of Hamilton circuits here in a complete graph, now what can you do? It's like you have one, one, two, three, four, and so on. Again n, and then you're coming to one. This is one. Okay. Suppose if you want to look at the some other Hamilton circuits here in a complete graph, from every vertex to every vertex we have a connection. Therefore, it is nothing but arrangement of these numbers. That's it. How many ways can you arrange these numbers? Okay, assume that in which the starting and ending points are fixed. Suppose if you want to count the number of Hamilton circuits which starts at 1, okay, and also ends at 1, then how many Hamilton circuits are there which starts at 1 in a complete graph? Are you sure? Are they n factorial or n minus 1 factorial? Be careful. I am asking all Hamilton circuits which starts at 1. See, the first and last place are dedicated for 1. Now, in the middle, how many numbers we have? How many numbers we have? We have n minus 1. So, in n minus 1 factorial ways, we can arrange it. These are the number of Hamilton circuits starts with 1. So, like that, for every number, we can have n minus 1 factorial Hamilton circuits. Okay. So now if we add all of them, then it's like n minus 1 factorial needs to be added. How many times? N times it needs to be added. Therefore, n into n minus 1 factorial, that is n factorial. Okay. So this is the answer for the number of Hamilton circuits starting with 1 or at any point or at a fixed point. Okay. Now, if you want to look for the number of Hamilton circuits, then I can say that n factorial are there. Oh, wait. Ah, yeah. If you treat the starting point as different, then fine. I can say n factorial. I can say n factorial. But these are all isometric. If you observe, all these n factorial Hamilton paths are isometric. You will get a cycle. That's it. Now, there is a sufficient condition for existence of Hamilton circuit. So you take a simple graph with n vertices, where you have more than 3 vertices, such that degree of every vertex is at least n by 2. It means, for example, if I take a graph with 4 vertices, make sure that the degree of every vertex is at least 2 or more. Okay, I hope in the earlier graph that I have drawn, this one, you can see that I'm taking 6 vertices, right? So if you see the degree of each vertex, it is, oh no, I'm taking 6 vertices here. It is 3. I'm having less degree vertex also. Anyway, this is a sufficient condition. Okay, it is good to call this example here. See, this condition is sufficient but not necessary. Okay, this is an example which illustrate that this condition is not necessary if the graph has Hamilton circuit. Okay, for example, here you see that the number of vertices are 6, but you see degree of a vertex, you can find a vertex whose degree, for example, degree of 5 is 2. which is less than 6 by 2. Okay, so now this example illustrates that it is not necessary. Okay, so this condition is not necessary. It is only true in one way. If you consider a graph such that every vertex has at least degree n by 2, then the graph has Hamilton circuit. Okay, now let me do one thing. Let me take a graph with 6 vertices. What if I take an odd number? Fine, let me take an odd number. So in the odd number case, what is it? 5 by 2, that is 2.5. So we can't have a vertex with degree 2.5. So you must take a 3 degree. Okay, so let us construct a graph with 5 vertices in which the degree of each vertex is 3 or more than 3. I hope you can see that. But this vertex degree is 2. This vertex degree is 2. But anyway, without having that condition, I am seeing a Hamilton path here. Sorry, Hamilton circuit here. What is that Hamilton circuit? You can travel from 1 to 2, then to 3, then to 4, and then to 5, and then you'll come back to 1. Alright, let me do one thing. Let me break it. Suppose if I break it, do we have any Hamilton? Yeah, I hope we have 1 to 5, 5 to 2, 2 to 3. No, do we have? Let me see. 1, 5. No, right? Because 1, 5, 4. And then if you come to 3, at max you can go to either 2 or 1. But if you go to 2, it means you're leaving the vertex 2. If you go to 1, right? So how about 3, starting at 3? Let me see. 3, 4, 5, 1. Yeah, now there is a problem. From 1, so we can't establish connection here, right? Okay, because that now I hope this one can be taken as motivation for the hypothesis of the theorem. Like why they are saying that at least every vertex is of degree n by 2. Okay, you see that there are 5 vertices and its degree is 2, and even the 2 degree is also 2. Okay, and we are getting problem with these 2 points only. Now let me do one thing. Okay, let me make this as degree 3 by connecting 2 to 4. Let me connect this to 2 to 4. Now can you find a circuit? Still there is one vertex with degree 2, but however, just by adjusting that, can we find a circuit here? So let me see, what is that circuit? Yeah, I hope I can see the way. 4, or let me start at 3, 4, 5, and then 5 to you come. Okay, I'm not finding it. That's not, because if I come to 2, then there's no way to move to 1. Okay, it's not good. let me start at 2, 2, 3, and then to 4. What is it you're giving? 1, 3, 2, 5, 4, 1. Is it 1 and then to 3? Okay, 2, yeah, 5, 4. Yeah, you'll come back to 1. Yeah, correct. It has. Yeah, one more is given. What is it? 2, 5, 1, 4, 3, 2. 2, 5, 1, 4, 3, 2. Yeah, correct. Yeah, so we have many Hamilton circuits here. Nice. Okay, but without, if we don't have this edge, we are not able to identify. This graph does not have any Hamilton circuit, right? Okay, so now this Dirac theorem gives us a sufficient condition to have a Hamilton circuit. Okay, so now how you need to use this theorem as, you just check degree of every vertex. If it is more than n by 2, where n is the number of vertices, then you say that it has Hamilton circuit. Suppose if G do not satisfy this condition, then you can't make any comment on it. Do you understand why? Because this condition is sufficient but not necessary. Alright, this is an example. This graph G is not satisfying hypothesis of the theorem, but still it has Hamilton circuit. Okay, so use this theorem to say that Hamilton circuit exists. You cannot use this theorem to say Hamilton circuit does not exist. Okay, so it is helpful in one way only, not in two ways. Similarly, let us see what is the sufficient condition for Hamilton path. And that to remember one thing, these theorems are applicable for simple graphs only, not for multi-graphs. Even the earlier theorem, it is stated for simple graph. Okay. Now let us think about theorem which gives sufficient condition for Hamilton. Oh, this is also for Hamilton circuit, not for Hamilton path. Don't we have it for Hamilton path? Just a minute. But remember one thing, having Hamilton path, it is same as having, having Hamilton circuit, it is same as having Hamilton path. You know why? Because if you have a circuit, let's say it starts at A, B, C, D, E, and then again, let's assume that it's coming back to A. Right? Now, what you can do if you want Hamilton path, you can simply stop at E. That's it. This is a Hamilton path. Okay, so every Hamilton circuit can be treated as Hamilton path also by not traveling to the same edge again. Okay, so these theorems can be used as sufficient condition for Hamilton paths also. Okay, so what is one more sufficient condition for Hamilton path? So you start with a simple graph with more than 3 vertices. So for every pair of non-adjoint vertices, for example, you may take A, B, C, D, E, F. Alright, for every pair of non-adjoint vertices UV, you need this condition, that is degree of U plus degree of V is greater than or equal to N. Then we can guarantee that there is a Hamilton circuit in that graph. Okay. So here, let me look at this graph. Is it satisfying hypothesis of this theorem or not? Let me see. First of all, let us identify pair of non-adjoint vertices. So what are non-adjoint vertices? I hope you can see this graph as bipartite, isn't it? This is not, okay. Let me assign two different colors. No, this is a bipartite graph. Yeah, but it is not complete bipartite graph because from C to D we do not have H. Okay, now we can easily identify a pair of non-adjoint vertices. What are they? You can take AB. So you can take the pair AB. They are non-adjoint. Even the pair BC, they are non-adjoint, and AC. Okay, so these are the non-adjoint pairs, and we have few more pairs also. We can take EF, ED, and FD. So is it satisfying hypothesis of the theorem? This graph. So for that, what I need to see the degree of A plus degree of B. Okay, let me write the degrees here. A degree is 2, B degree is 2, C degree is 2. I hope it is not. It's not satisfying hypothesis of the theorem. And the degree is 2, and the degree is 2, the degree is 1. Anyway, it has one pendant vertex. Since it has one pendant vertex, we cannot find a Hamilton circuit. Okay, but however, even if I look at this degree of U plus degree of V, when U and V are non-adjoint, it is not greater than or equal to 6. So this graph is not satisfying the hypothesis of the theorem. Okay. Now we cannot say that G do not have Hamilton circuit based on that. What this theorem says is if a graph satisfies that condition, then you can say it has a Hamilton circuit, but not the other way. If it is not satisfying the condition, it doesn't mean it do not have Hamilton circuit. For example, if I connect C to D, let's assume. Okay, so let me connect C to D. Now I hope we can find a Hamilton circuit. What is that Hamilton circuit? Having an extra edge between these two. Can you tell me Hamilton circuit here? What is path from A to E? Is this about this question or? So D A E B F C D. So going from D to A, then to E, okay, E to B, and B to F to C, and then you're going back to D. Yeah. So we have a Hamilton circuit, but it's not satisfying hypothesis of the theorem. Okay, and this is also an example to say that this condition is not necessary. This example illustrates that the above condition is not necessary. It is just sufficient. If a graph satisfies this condition, I can say that it has an Hamilton circuit. But if it is not satisfying that condition, we cannot comment anything using this theorem. Okay, even if the graph is Hamilton circuit, then also we cannot say that it satisfies this condition. Okay, right? So Ore's theorem is a sufficient condition, but not the necessary condition. Okay, this is named as Ory's theorem. And how about the previous theorem, Dirac's theorem? All right. So determine whether the given graph has Hamilton circuit. If it does, find such a circuit. If it does not, give an argument to show that. Yeah, how about first graph? Does it have any Hamilton circuit? No, because the strong reason that we can give is C. Okay, if you look at C, let's say you start at any point, this C needs to be visited twice if you want to travel through all vertices. Okay, even the F also needs to be visited twice, right? So the reason we can say that this C and F needs to be visited twice to create a circuit here. All right. Okay. How about second one? Does it have any Hamilton circuit? How about Hamilton path? Circuit is okay. It doesn't have circuit. Does it have Hamilton path? First example. First example. Yeah, Hamilton path. It has Hamilton path, correct? Because you can travel from B, A, C, F, D, E. So that way we can travel. Yeah, it has Hamilton path, but not Hamilton circuit. So how about this one? I hope we can easily see when there is a cycle, then we are done. So this has both Hamilton path and Hamilton circuits. Okay, saying that it has Hamilton circuit, it is same as saying it has Hamilton path also. But the other one is not true. Having Hamilton path does not guarantee Hamilton circuit. Example is this, first example. Okay. Now next one is looking interesting. It seems like the structure that we see in game. Which game? Daddy game? Yeah. Alright. So does it have any Hamilton? Can we say every Hamilton circuit as Euler circuit? No. How can every Hamilton circuit can be in Euler circuit? No, no. Now we can see an example. Alright, let me show you an example which has Hamilton circuit, but that is the Hamilton circuit. Like whatever I have drawn, that itself is a Hamilton circuit, right? Now you see, now having this edge here, A, B, C, D, E. Now the Hamilton circuit here is not an Euler circuit. And the Euler circuit here is not a Hamilton circuit. This graph has both circuits, Euler circuit and also Hamilton circuit. Alright, let me write Euler circuit. So Euler circuit, it means it needs to travel to all edges. Okay, let me concentrate on Euler circuit starts at A. Okay, so that is A, E, D, A, on. So there are two terms of odd degree. A, E, what are the degrees here? So we can have an Euler path, not Euler circuit here, because not every vertex is of even degree. It has no Euler path. Okay. Oh, sorry, circuit. Okay, let me do one thing. Let me introduce one more edge. Yeah. Now on one more edge. So that the degrees, again the problem. This has degree 3. So I need a graph which has both Euler circuit and Hamilton circuit. Suppose if you take a cycle Cn, Cn has Euler circuit and Hamilton circuit, both are same in this case. But I'm looking for an example of a graph which has Hamilton circuit and Euler circuit, but both are not same. We have Hamilton circuit, no, but there's no Euler circuit here. That's the problem. Because for Euler circuit, we have necessary and sufficient condition. That is, every vertex must be of degree 2. So even degree, not degree 2. But here the degree of A is 3 odd. So I can't have an Euler circuit. So let me do one thing. Let me try to create one more edge. Yes. Now let me look at this graph. Degree of E is 2, degree of A is 4, degree of D is 4, B is 2, and C degree is 2. So every vertex is of even degree. There is an Euler circuit. So what is that Euler circuit? Right, let me write that Euler circuit here. That is, let me start at A. Then you can go to E, alright, and then D, E, B, C, D, and then back to A. Yeah. You see that? First I traveled along A to E, this one. And next E to D, and then D to E to D, and then what is it I have written? That is D to A, sorry. This is D to A. So this is D to A, and then A to B, and then B to C, and C to D, and then finally D to A. Yeah. So we have Euler circuit. But remember, see this. This is not Hamilton circuit. Because the vertex A and the vertex A is repeated, and not only vertex A, D is also repeated in the Euler circuit. Okay. Now let me write Hamilton circuit here. What is Hamilton circuit? That is simple: A, B, C, D, E, A. That's it. This is the Hamilton circuit. So here, Hamilton circuit is not same as Euler circuit. Now I have a question. Can we have an Euler circuit which is also an Hamilton circuit for it? Is it possible? Is it possible? Oh, tell me what is that circuit? It means I need a circuit here which is both Hamilton. No, I am asking in this graph. I am not asking for an example of a graph which has same Euler and Hamilton circuit that I already told you. Cn has both Euler and Hamilton circuit. I'm asking in this graph, in this example, can you identify a Hamilton circuit which is also an Euler circuit? I'm asking in this example. A, D, B, C. A, D, What is ADBC is not not at all a circuit first of all. ADCBA. ADCBA. But you are not involving E in it, no. E is not involved, therefore it cannot be Hamilton circuit. Every vertex needs to be visited. Here in this sequence, the vertex E is not visited. Alright, I hope the answer is no. You cannot find an Euler circuit here which is same as Hamilton circuit. Okay, you try to investigate. You try with examples. I mean, writing the all possible Euler circuits. Yeah, not possible. What is the reason? A B C D E A. A B C D E A. Is it? A B C D E A. But you're not traveling on this edge, you know. This edge you forgot. This is that is Hamilton, but not Euler, because this edge is not taken care. You understand? I hope the simple reason that we can give here is, if you need an Euler path, then definitely this vertex D needs to be visited more than twice. Sorry, more than once, because it is of degree 3. Okay, and also here you have a vertex of degree, so not, okay, it is of degree 4, right? Not 3. Even if you have degree 3, if you want to cover all the edges, that vertex needs to be visited more than once. So for example, in the Euler path that we constructed, how many times D got visited? You can see that it is visited 2 times. And it is of degree 4 and it got visited 2 times. Do you understand why? Because you have A here, the junction A. You want to cover all the roads which is connected to this junction. Alright. So in one way you can go like this. So once you visited A, and next you can go like this. You visited A. It means at least twice you need to travel. Even if it is of degree 3, okay, this A needs to be visited twice at least. For example, one time you may travel like this, fine. Okay, the next time you need to utilize this edge, no? So definitely you need to come back to A. So we can clearly say that it's not possible to construct an Euler circuit without visiting A twice if it is of degree 3. So that says that the Euler circuit cannot be a Hamilton circuit here, because in the Euler circuit here, this vertex needs to be repeated. Not only here, in any Euler circuit, you take any vertex of degree 3 or degree 3 or more, it needs to be visited more than once. Okay? So that is the strong reason we can say that. Alright? So I hope you understand these Euler circuits and Euler. But I think I didn't discuss this problem. What is the problem here? The problem is determine whether the given graph has Hamilton circuit. Yeah. How about this? Does it have an Hamilton circuit? Some are saying no and some are saying yes. What should I stick to? I'm not asking about Euler path or Euler circuit. I'm asking about Hamilton circuit. All right, let me see. Starting at A, I would like to see A, B, C. And then how do you go? Okay, then I'll move to Q. We need to give a strong reason to say it has no. There will be no vertex left. What do you mean by that? Third condition says we can't contain a smaller circuit within it. Okay. Let me see what is that condition. Hamilton circuit cannot contain a smaller circuit within it. But seeing this picture, you can't say that these are all the circuits which lies inside. That you can't say no. For example, what if I travel this way, I to J, then to K, then to Q, then I'll come back to P, and P to M. But it cannot be Hamilton, because if I go the other direction, it is not. Using third condition also, I don't think so. We can say it's stronger. No, because what are the other two conditions we have? Every vertex of degree 2 needs to be visited twice. I mean, every edge which is incident with degree 2 vertex must be visited. Okay. I think that we can use that condition. Now let me see that the A has degree 2 and C has degree 2. Even G, E, N, L, K, I. These are all has degree 2, right? Now here, if you construct a Hamilton circuit, then definitely all the edges which are incident with these degree 2 vertices must be visited. Okay. Now let us go with an assumption. Let us go with an assumption that in the path these two are visited. So I'm taking an assumption. Okay. So these two edges are visited. We traveled, and also we traveled on these two edges, and we traveled on these two edges. Okay. And now, if you travel on these two edges also, then what happens? Then this B, at least one point here needs to be visited twice. At least one vertex. For example, I am starting at A. Okay. Then B must be visited twice. Do you understand? Because we cannot stop our circuit here just with B. We need to go inside. We need to cover the inside vertices also. Okay, so definitely if you want to cover the inside vertices, and with a condition that every vertex incident with degree 2 must be visited, I mean every edge incident with degree 2 vertex must be visited. With that condition, I can say that there is at least one vertex in the outer layer that has to be visited twice. The moment it is visited twice, that cannot be a Hamilton circuit or Hamilton path. Do you understand? So that is condition for Hamilton circuit, I hope, not for path. So see the condition. If a vertex of a graph has degree 2, then both the edges that incident with the vertex must be part of any Hamilton circuit. Okay, so using this condition, I can say that this graph do not have Hamilton circuit. Okay, but how about Hamilton path? Do we have Hamilton path? What is a Hamilton path? Tell me. I hope I'm finding it. Right. So I hope we can start at this point, maybe at K. Now I'm thinking about Hamilton path. Okay. So is it good to start at K? or at P? Not good. Okay. How about at P? Do we have Hamilton path? Okay. Now, what is the strong reason we can give here? Like on what basis we say it has no Hamilton path? Suppose if I don't have that P, then okay, we are sure there is an Hamilton path. Of course, we draw. Okay. So I hope now I can talk about these vertices. This is a vertex of degree 4 and this is a vertex of degree 4. You think of any Hamilton path which which starts at P. Okay. So if any path starts at P has to visit one of these 4 vertices at least twice. Can we give that guarantee? I'm thinking about the path. First you complete inside and the latter going outside. That's the path I'm thinking of it. But without that, like you go this way and this and here, then come here. Okay, but now you cannot travel back to I. That's the problem. If you travel back to I, then you need to move to J. Okay, so this got visited twice. That's it. Next, let me think about other path. Not going straight. You go to I, you come here, then here, then here. Okay, go back and to here, next to here, here. Yeah. Now again you need to visit I more than once, right? Okay, so without going towards I, let me do one thing. Let me come down to N. Now you cannot visit this I at any cost if you travel this way. Okay, so we have a vertex of degree 4. How many vertex? 1, it's not. 1, 2, 3, 4. So whatever path you construct, which passes through all points of the graph, all vertices of the graph, then that graph needs to visit at least more than once. I mean, it needs to visit at least one of these degree 4 vertices more than once. So what I'm saying is, you take these vertices, that is O, J, M, Q. These vertices needs to be visited more than once. At least one of these vertices. I'm not saying that all vertices needs to be visited. At least one of these vertices needs to be visited more than once if we construct a path going to all vertices of the graph. Okay, I hope that is the reason we can give to say that there is no Euler path, sorry, Hamilton path. Okay, so now I will stop it here. So the next concept what we have is planar graphs.